Hello everyone, welcome back. We're doing problems on static equilibrium, that is net torque being equal to zero, as well as net translational force being equal to zero as well. Now this example 11.7 is a little, well I think it'll make sense to you, but we just need to sort of sort out what's going on right here. So we've got a hiker who has broken his forearm, all right, so this forearm, which actually has two bones in it, that's the radius and the ulna, all right, so there's two bones in there, doesn't really matter, but that, in order to kind of get it to set, or to at least keep it safe, you have to apply some compression to it, all right, and so a lot of times what you do if you break your forearm is that you put it in a sling. What the sling does is it applies tension upwards to the shoulder where it's slung over. All right, and since that tension has an X component directed towards the elbow right there, it's causing compression in along the forearm, which I guess supposedly is supposed to make your forearm set, and if you've broken it. Okay, so we've got temporary sling right here to kind of describe why this sling is slung up like that. So it produces an upwards tension that creates compression on the forearm right here. Let's put our values in and see what we get. So this angle right here, 40 degrees, that's this guy right here, which we already have. All right, so that theta, you might say, is our 40. Attaches from the hand up to the shoulder. One thing we need to assume is that the mass of the arm is uniform. Now, you know that it's actually not. I mean, I guess you call this your upper forearm is usually bigger than your wrist and your hand, but just pretend that it is. We're considering them to be uniform. So the whole mass of the forearm is 1.30 kilograms. All right, and that length right there, we'll just call it L. That is 0.300 meters from here, L, to there. Okay. We want to find two things. A, we want to find the tension in the cord, or the strap, or whatever is attaching the arm to the shoulder, okay? Tension we want to find, which probably means we're going to need to find Tx and Ty. Then we're also going to need to find B, force X and force Y. This force right here at the elbow. Because if you think about it, if your elbow wasn't attached to your arm, if your elbow just was allowed to slide, if there was a sideways compression force caused by the tension right here, the person's forearm would slide that way and kind of come off your elbow. Well, we know that doesn't happen. So the elbow is actually, you might just say this little hinge joint right here is applying a force back to make sure that the arm doesn't, fall out of its elbow socket, okay? So we want to find this Y component and F component of that force that the elbow is directed towards the center of that that tension force right there, okay? So that's the plan, at least. So let's see if we can solve for, well, we're asked to solve for the tension first, all right? So let's just go ahead and do that. If we can find one of these components, finding the tension should be easy, right? Because we have this angle right here. So let's see if we can, if we want to find one of these components, we can't put the axis of rotation right here because that's where the force is that we want to find. So we're going to put the axis of rotation over here so that we can be told about these components of the force. All right, I'm going to shrink this down a little bit now that we're all set on what to do. So, so for part A, the tension, that's what we want to find, all right? Well, let's write a statement about the net torque around, I'm going to say right there is the axis of rotation, okay? Well, in the positive direction, right here, so here's our axis of rotation. In the positive direction, we have Ty acting upwards, right? Ty, the Y component of the tension, is acting up from the palm of the person's hand. Does Tx do anything right here? Well, it is a force, but it's directed right at the axis of rotation, and so it doesn't have any real radius, right? It's right on line with the axis of rotation. Ty is at right angles to it, so that'll make it easy to find that torque created by Ty. What distance is Ty from the axis of rotation? distance L, right? Which we know, which we're told from the problem. Oops, I don't want to put an equal sign. I want to put a minus sign, right? Ty is acting upwards, creating a sort of counterclockwise rotation, which we call positive. What is acting downwards? Well, the weight of the arm, right? If your arm didn't weigh anything, then you wouldn't need to put it in have a sling hold it up. So what is the weight of the arm? It's this mg right here. And we can consider the weight of the arm, mg, to be acting right at the very center. And remember how we said that we're going to consider the whole arm to be uniform, even though in real life it probably isn't. We're going to consider it to be uniform, so mg is going to be acting right in the center right there. So what distance is mg from the axis of rotation? It is distance L divided by 2. Okay? And since we know that the net torque is equal to 0, unless you want your forearm to be like swinging around in circles as it's broken, which you don't, then we can say, all right, well, all these are going to have to be equal to 0. So if Ty times the length minus mg times the length over 2 equals 0, then I'm going to add mg times L over 2 to the other side. So we're going to have a statement like this. Ty times L. That should be drawn a lot better than that. Ty times the length equals mg times the length divided by 2. All right? Well, we're solving just for Ty right here. Actually, we're solving for t, but if we get Ty, that should be no problem. So Ty is going to be, actually, what can we do here? I was going to divide the L down, but then I realized, hey, there's an L on the other side too. So that's just going to cancel out. We don't need to worry about dividing it at all. Okay, so it's going to be mg divided by 2. What is our mg? Well, our mass is 1.30 kilograms. 1.30 kilograms times our 9.81. Divide that by 2. That's going to get our tension in, you might say our y component of tension. 1.30 times 9.81 divided by 2. 6.38. 6.38 newtons, right? Well, that's helpful, although it's not our final answer. We want our t, right? Well, so we know that Ty equals t, the full magnitude of t, times the sine of the angle theta right there. And we know that theta is 40 degrees. So t, of course, is going to be Ty divided by the sine of theta. That is, Ty is 6.38 newtons divided by the sine of what's our angle? 40 degrees. All right, and that, dividing that out, gives us a grand total of 9.94 newtons. That is this tension that is acting towards the center right there. This, that guy right there, that's our T, that's our tension, acting towards the shoulder. All right, so it's pulling up, but it's also pulling in, which you want it to do because you want there to be compression on the bone so it will set right. Okay? Part B. Part B, actually there's two parts to Part B. We want the X and Y component of that force from the elbow directed towards the center, the sort of counteracting that tension force by the string or the strap right there. Okay, what do you want to solve for first? Well, let's just solve for, I don't know, X. I think X will be somewhat easy. Okay, for F X, the X component, all right? Well, we can say that the net force in any direction, but particularly the X direction, equals 0. And so we can say the net force in the X direction is, well, you've got this X component right here, which is what we're solving for, Fx. And what else is acting in the X direction? Tx, right? The X component of this pulling backwards. Those two forces acting toward the center create what we call the compression that is required to let your forearm, your broken forearm, set straight. Okay? So that's acting in the positive direction, we'll say. And the negative direction is Tx. All right? Well, if those equal to 0, like we're told, then that means that Fx equals Tx. And Tx, well, we know what T is. We know what Ty is as well, but T is going to be well, Tx is T cosine theta, so that's going to be 9.94 times the cosine of 40 degrees. In fact, I'm going to save some space. I'm going to write it down below. Squeeze it in there a little bit. So that's 9.94 cosine of 40 degrees. All right, what do we get? Times cosine 40 degrees, 7.62 newtons. That's the x component of this force from the elbow right there, okay? Acting inwards. Excellent. So we have the x component. We have now the y component to solve for. So for force y, this guy right there, what is that? Well, we can use our assumption that the net force in the y direction is also 0 and say, all right, well, what are the forces acting in the y direction? We say there's no translational motion in the y direction. So what are those forces acting in the y? Well, there's Fy, which is what we're solving for. Mg is acting downwards. And Ty, I'm going to put a plus there because Ty is acting upwards. If these all equal to 0, then we should be able to say by adding over our mg and subtracting our ty, then that's going to be Fy equals mg minus ty. All right, the y component, both of which we know. Mg is, what is the mass? 1.30 times 9.81. We're going to subtract from that, and get a better subtract sign here. We're going to subtract from that ty, which we found way up here. Here's the ty, right? That's what's acting upwards. That's up, that's down, that's up. So we're solving for Fy by plugging in ty right here. That is 6.38 newtons. 6.38 newtons. And that's going to give us our final Fy, which is what? 1.30 times 9.81 minus 6.38. 6.37. 6.37 newtons. That's what the y component is of the force from the elbow right there. All right? So we found our tension in this line, and we found the x component and the y component. If we really wanted to, we could put these together and use the Pythagorean to find the full force exerted on the center from the elbow, because the elbow is experiencing a force right there. But we don't have to because that wasn't what the problem asked. Plus, I ran out of space. So that's going to be it for 11.7. Thanks for following along. Make sure you ask me if you have any questions, and I'll see you on the next one.